Remember, a codon is a triplet. It takes 3 to create something. So if I have the sequence that has 10 codons, that's 30 nucleotide bases, and I add 1, do you see that all of them are now out of order? They all moved over by 1 position, which means that none of the other ones upstream from where I just placed that are going to read properly. Adding 1 destroys everything in the entire gene. You can't add 1. If you add 2, it does the same thing. They're all off by 2. You won't get the same amino acid.
Yeah.
If you add 3, and you actually put enough in there for a full codon, you still screwed it up because now it can't fold together properly. And I see how just little changes over long periods of time. That's all it takes, Gavin. Okay. Yeah. Not a chance.
Yeah.
Not a chance.
Ladies and gentlemen, welcome back to the It Stands Written podcast. My name is Braden and I'm with Gavin. We are still in our series on creation versus evolution. So in the previous episode, it was titled Not a Chance. We did part 1. Today we are doing part 2. On the last episode, we talked about what information is, and we briefly touched on the difference between information that's just information that doesn't mean anything versus information that has meaning behind it. So Gavin, you're going to take us into part 2 and explain to us how this proves and shows that there is a God who designed it all.
Yeah, thank you again for the chance, guys. This is part 2 of what I think will be 3 parts. We'll see how far we can get. But to clarify, information that's merely information, often known as Shannon information, is the sort that bears some kind of information capacity, but doesn't necessarily convey a signal. So when we gave the example of Scrabble letters being dropped in random positions, it certainly has the same amount of information bearing capacity that when they're arranged in a particular sequence, a specific sequence, they convey something more, right? And so that is the distinction between, say, Shannon information and functional information or specified information. We're going to get more into that today. So if you guys didn't hear the last one, I suggest backing up or you're going to be way behind. The other thing too is, guys, these things didn't come to me instantly. And if they come to you instantly, good for you. But it's not a problem to go back and rewind this and just listen to it again. I will do my best to make all of this clear. So I want to talk briefly about the shape of the DNA molecule and give you guys a little more understanding. See, it's hard in a podcast like this that's merely audio to tell you about complex structures, but I'm going to do my best. And you can actually Google along as we go for anything that I describe. So the DNA is probably the most common, I mean, in art and all kinds of things, it's seen commonly, and it just looks like a spiral staircase.
Right.
Okay. If you were to unwind it, make it look flat, it appears like a ladder.
Mm-hmm.
If you look at a ladder, you have the sides of it you can grab onto, known as the rails. And horizontally, you have the steps, or the rungs we'd call them, that go from top to bottom. That is the shape of this molecule. Okay, it looks like a ladder. What I'd like you to imagine, though, is instead of this being a normal ladder, this is a rope ladder, so I can twist it and turn it into what would look like a spiral staircase. As those rungs turn perpendicular to us, suppose that we were facing it like a normal ladder, it's parallel to our chest, now it turns perpendicular.
Mm-hmm.
When it does that, it looks like a very thin area, and then it widens back up as it becomes parallel to us and goes thin again and back and forth. A complete revolution is about 34, the distance would be about 34 hydrogen atoms to go from one starting point to the next rotation above it. Okay.
Mm-hmm.
The width of this thing is about 20 hydrogen atoms. So just to give you an idea of scale, this is pretty small stuff.
Right.
What you will find, though, is if you look at pictures of DNA, some of them, of course, they're all mostly models. There's a few little scanning electron images of it that are pretty cool. It looks like almost like a screw. It's very, very tight. But some of these images you look at are more accurate in their drawing than others. And here's what I want you to look for. If it goes from wide to narrow and wide to narrow and wide to narrow, and every wide space is equal to every other wide space, there's a problem. The real DNA molecule doesn't actually look like that. It has what they call a major groove and a minor groove. So the width of it alternates between being very wide and being not so wide as it goes back and forth, and it just has to do with the way that things are arranged inside of it. Okay. The sides of that, what we call the rails of the ladder in essence, are the sides of it, or what we would call the rails, are external and the information is internal. Okay. So the information is not sticking out. When they tried to figure out what this molecule looked like, and this is back in the 50s, if anyone had this assumption that DNA was just a mere chemical substance, and you might say it is a mere chemical substance, it really misses the point, because this is actually carrying information. It's different and it's unique. And so the assumption was the information that it bears in those alternating sequences of digital code in nucleotide-based form would have to face out. Okay, if they were facing towards the center, how could they be read? Because they're concealed by the very spine that holds it all together. Well, we'll get more into that later, but the truth is they face in, not out. The information fits in a very small area. And the reason it was important to mention that there's a wide groove and then a lesser wide groove, they call them the major and the minor, is because to store this information tightly, it is wrapped around a spool known as a nucleosome spool. Okay, so what you have here is a very highly specified pattern of matching positive and negative charges, which allow this very information-rich DNA to wrap tightly around these histone proteins. They call it nucleosome spooling. If, for example, the wide area and the narrow area weren't accounted for, you'd have bumps in all kinds of places where it didn't align correctly. Just think about, coiling up a garden hose and trying to make it look perfect. You want every little bit to fit within the, narrow part of the next one, right? And the gap between them. Yeah. From there, they bind up tighter into what make up the chromosomes. That's why we said there are at least 700,000 gigabytes per gram of information-bearing capacity in this molecule. And again, that's probably very, very much on the low end of the scale. We believe it to be considerably higher than that. Now, going back to the ladder analogy for just a moment, let's pretend we're facing it again and it's straight, okay? And in the middle of this ladder, the rungs in the very center are bonded together by a magnet, which means you could snap it apart and it would split right down the middle, but you could also bring it back together and they would immediately sync back up to one another, okay? Yeah. If you're staring at this ladder and we're looking at the right-hand side of it, this is the right rail of the ladder. At the very top, we're going to refer to that as the 3' end. And at the very bottom of that same side, we're going to refer to it as the 5' end. Now, on the other side, just the opposite is true. The top is the 5' end, and the bottom's the 3' end. This matters because there's a particular direction this code has to read inside of it for it to be functional. You can't read it backwards. It won't produce the same thing. It'd be like trying to read a book backwards and hoping you could still understand the content. Okay? So what we have is a process known as transcription. And it's really easy to remember what that means because it's the word transcript. A transcript is a copy of something. Someone might transcribe this onto paper and say, here's a copy of what Braden and Gavin talked about the other day. Right. The information inside of that DNA molecule is transcribed. It's copied. To do this, there's and we actually mentioned this, we gave honorable mention to a protein called RNA polymerase back in the first episode. And it has the job of making a transcript. The way this thing works is inside the nucleus, depending on whether or not we're dealing with a prokaryote or a eukaryote. This thing, it exists in both, technically. It's not always in a nucleus. One may be absent. But what its job is to slide down the spine of the DNA, and it will unwind it, uncoil it, and separate it so the ladder is now open and you can get to the information that's on the inside of it. What it does is it creates a copy of what the other side would have looked like. Since the A and the T always match up, adenine and thymine, and the C and the G, cytosine and guanine, always add up. What they do is they create the other side. For example, let me say it this way. You could know what the other side looks like without seeing it because it's always the same pairing of bases, right? That's how this works. Mm-hmm. So what it does is it creates a transcript of what the other side is. And it reads it from the 5' end to the 3' end. So there's a little region inside where it's been split and it's being copied where there's a hybrid between what we call DNA on one side and RNA, which is the copy on the other. It looks just like it. The only real difference between RNA and DNA, other than one is single-stranded and one is dual-stranded, is that the thymine is switched with what they call uracil. Okay? That's the only difference. So it creates this little strip or transcript of a linear digital code, and then it exits wherever it's at and is brought quite a long distance by cellular standards to what's known as the ribosome. Now, what happens is these little digits, these digital characters, A, C, T, G, or in this case, A, C, U, and G, because it's RNA, create a special code. Every bundle of 3 in sequence is what they refer to as a codon. So, for example, if you had C, A, G, that would actually code for a particular type of amino acid. Okay. If you had UCU, it would code for another. There are about 20 different varieties of these. Mm-hmm. Other patterns are going to just say, this is the end, stop here. Don't transcribe any farther because now you're getting into something else that you don't need, right? There's other ones that are promoter sequences that say, this is where you need to begin because if you start too soon or too late, you're going to have part of what you need or more of what you need, and it's going to be a big problem. We need the exact copy for things to work. There are proteins that are going to increase or decrease the usage of any of these gene segments to say, hey, here's what the cell needs right now. It's a little low on one substance, so create a protein that will be useful for that, or don't create one because we have too much of it, whatever the case is, and it chooses. Mm-hmm. So if you go online and you look at the code, you may find that there's actually more than one. Okay. It's not universal. There are about 15 of these different codes that have been discovered, just like there's multiple languages, and each one that you could technically, there's languages that use our characters of our English alphabet, but they're not the same words. Look at Spanish and English, for example. There are 15 languages that we know about, potentially more within DNA, that are doing all this stuff. So essentially, one code is now going to create a second code. The first code that you had in that linear sequence is going to be used to create a second code that now chains together amino acids. So when it moves from the first position in the nucleus, or wherever it was, to the ribosome is where it's going to do something known as translation. Translation is going to literally translate. We talked about multiple languages, that kind of thing. It's going to take the information in this digital format, and it's going to it's going to translate it into something that's useful to create an object. So I'd like you to imagine this for a second. This little strip of RNA that's a copy of the DNA that it just worked on, that it came from, is going to look something like the little flags you see at a birthday party that are hung from a string. Maybe you see them around a car dealership because every single day there's a sale, right? Mm-hmm. And these flags, if there's no wind, are all pointing down. Okay, so imagine that you have from left to right a big long strip of, say, 1,000 digital sequences of nucleotides, right? And a nucleotide base is not pairs, just a single side. And they're all facing down, just so we're on the same page here. What happens is if I have a sequence that says A, it will match up only with another sequence that says U. Uracil's the only thing that'll match up. If it tries to contact something else, it's not gonna fit. Mm-hmm. All right. So because it's sequence specific, there's something known as a transfer RNA. What I'd like you to picture, some people have said it's like a clover. I think it's kind of like a cross, really. It's a RNA strip, but instead of being straight like the one that I just described, this one folds in on itself. And it has two arms sticking out, basically, a top and a bottom. So imagine a cross. That's basically what it's shaped like. Mm-hmm. On the sides that stick out, where the hands would go on a normal cross, like crucifix, for example, there's nothing. On the top, there's anticodons. Anticodons essentially are three corresponding letters to match up with the letters on the RNA strip. Okay. They're called anticodons because they contact the ordinary codons. A codon, again, is a set, if I didn't already say it, I'm sorry, of three nucleotide bases. So if I had GUG, you could just sit there with a pencil and figure out and go, okay, that's only going to match up with CAC. If I had AAA, again, it would be UUU. If I had UUU, it would be AAA. So the point is every three of these has to match up and find a transfer RNA whose anticodon is the exact opposite of it.
Gotcha.
If it's off by one letter, they won't fit together. There is a molecular ruler checking the distance between them to see whether or not they're a fit. And if they're not a fit, it rejects it. Okay. It's looking for one in that ribosome that will fit it perfectly. And when it finds it, at the other end of that cross, say where the feet would be pointed, is what they call a amino acid. Okay. Because they're going to correspond to this digital code in the exact order that they were prescribed to, these amino acids will stick together in the intended order. These amino acids will then one day, same day, very quickly, fold into what become proteins. So I want to just define what a protein is. A protein is a molecular machine. And I don't want you to think that I'm using an analogy or saying this is similar to what a machine is. This is exactly what a machine is. Mm-hmm. It has specific functions, right? It can, turn a screw like a screwdriver, like a hammer to bang something into place. These are molecular machines that have extremely complex functions. Okay, so basically the result of this process is a long peptide bonded chain of amino acids. Now, depending on which ones were chosen out of the 20 varieties, they're going to stick to one another or push away from one another, whatever they're going to do in such a pattern to create a 3D object. They actually fold 4 different times. So in their first step, they're just a big peptide bond, big chain, say it's, a few hundred sequences or whatever. And then they turn what's called a secondary structure. And it starts to spin around kind of like what you would see in a DNA, like, the spiral staircase kind of thing. From there, it goes to a tertiary structure and it begins to bend in other directions and become more complex. And then finally, it becomes a quaternary structure. And at that point, you have a complete protein. Okay. And all the shapes, of course, are designed to do particular functions. I'm going to give you an example of a protein. One is known as topoisomerase. Topoisomerase is a pair of scissors that flies downstream on a DNA strand and cleaves one side of it to allow it to unwind a little bit and then reattaches it. So if you think about a rope, if you twist it and twist it and twist it, at some point it binds up too tightly. The opposite is true if you try to unwind it. You can keep unwinding it on one end, but if the other end is, a long ways away from you, it's going to start becoming harder and harder to unwind. So topoisomerase literally flies down to where the stoppage is, clips it, lets it unwind, and then puts it right back together in the same spot. Topoisomerase 2 is also a pair of scissors that does the same thing, only it can cut both sides of the DNA, flip them around a whole turn, one rotation, and put them back together seamlessly. That's what it does. Okay. And topoisomerase is not able to perform the function of a polymerase more than a hatchet could perform the function of a soldering iron, right? In other words, this is using Stephen Meyer's words. It has a very particular function. It's only going to do that. It's not going to be able to do other things that the cell needs. It only does that. So if we look at a picture of an insulin monomer, you guys might want to look at that up online. This is a protein. And you'll notice that it has a irregular sequence of amino acids. It's got a shape that is pretty hard to describe. I'm not even going to give it a shot. If you went online, you see this 3D object rotating around, you'd say, how in the world would I describe this thing? I mean, it would be pretty hard to, if I said, take all day, I want you to write as much as you need to describe this, you'd realize it's pretty tough. In fact, you'd have to resort to code. You'd have to do it in that sort of way and say, okay, we've got to put X, Y, Z coordinates, where things are going to be, what turns they make. It's going to have to look like the kind of code you're going to get for a 3D printer. That's what it's going to take.
Right.
There's no discernible or repeating patterns in it. Okay. If it turns left, goes up, goes down, spins around, whatever, you cannot predict the next step because there is nothing in it that repeats. It defies any description by any general rule. That's what it looks like. Okay. So it's specific in a couple of ways. One, it's specific in its shape, and two, it's specific in its arrangement. Okay. The order of all of those little pieces that came together to make it fold up into what it is and what it can do. It has extremely fine tolerances. It's got a hand and glove fit. And at that, it actually fits together hand in glove with other complex molecules that conform to the opposite shapes of it. Okay. How does it do that? Well, it does that by following whatever pathway the code dictated it to follow, as did the other one that had the hand and glove fit to do the other side of it. Okay. So real quickly, step one, a copy of a gene, which is a segment of DNA, is created. Okay. That copy is known as mRNA or messenger RNA. And it's basically a blueprint, okay, for whatever the protein is that we're using, okay? It's going to float away from its origin and head to a ribosome, which is made up of a couple units, a small subunit and a large subunit. They come together over the top, and at whatever the promoter sequence is, they're going to find their way to the start point with the help of some other proteins, okay? It's going to slide down the spine of that from the 5' end to the 3' end, and along the way, it's going to take these transfer RNAs, and it's going to stick them one by one into position until it finds a match. And when it does, it's going to take the amino acid that's at the opposite side of it and detach it from the mRNA and attach it to the predecessor in the sequence. Or if it's the first one, it's going to hold on to it until another one catches up. So it makes a huge long chain. This huge long chain then folds into a protein. And now you have a molecular machine that works and does everything it's supposed to do. So the question again, guys, is where's the origin of the information in this DNA for the first life? How could it start? And that's what Stephen Meyer refers to as the DNA enigma. So we're going to go into something, if that sounded complex, my apologies. Listen a couple times, go and double check me if you'd like. The bottom line is, as difficult as that was to understand, we're going to cross a new threshold. In my opinion, this is another level. I want to describe to you guys what complexity is. Mere complexity. Mere complexity could be described like this. It's unspecific. It is disordered. It's the result of chance. It's random, and it's unpredictable. That is something that is complex. It has no underlying rule. It has no underlying algorithm. It is incompressible, and it is improbable. Okay, that's something that's complex. So, for example, the arrangement of all the little pebbles that make up the asphalt on this street that we're on are arranged in a very different pattern than the ones at the next street over. Okay, they are incredibly dissimilar to one another. It's very hard to say, well, this rock, I mean, just imagine taking a handful of sand and throwing it and watching the pattern out laid in on the ground. Every time you throw that, if you picked them all back up and threw them again, you would get something that is completely dissimilar from the previous attempt, right? That is complexity, all right? Incompressibility is one of its descriptions, meaning that it can't be described easily. You'd have to talk about every individual grain of sand, which side was facing up, what they looked like, how they were rotated relative to one another. And so for an example, I could say lowercase j, 8, lowercase h, capital X, 1, percentage sign, 4. If I said, okay, Braden, I want you to do your best to compress that so it takes up less space. It's going to be hard because the only two things in it that even repeated were 8, and it's probably going to take more description to say do it twice than it would to just write it down, right? The primordial soup would be a good example. This alleged place where there was the bubbling broth of complex chemicals that created life would have been a description of something complex, floating around, no particular order, just bumping into each other, random collisions, that kind of thing. Another example would be random polypeptides, not sequenced ones like we just talked about a moment ago that fold into something, important or useful, but rather random ones, all the 20 of them just being mixed around by the billions in a tank together. Okay. That is complexity. Now let's look at the opposite end of the spectrum. Things that are ordered. Things that are ordered are regular. They are redundant. They're predictable. They're also compressible. They're specific. That's the word we're going to spend a lot of time on. They're law-like. They obey some kind of underlying rule or underlying algorithm. They are very low in complexity. And they're described very easily. So an example would be 1, 2, 3, 1, 2, 3, 1, 2, 3. If I said, repeat that 1,000 times, guess what? I just compressed it into a small sentence and conveyed exactly the signal that I meant to. And you could take all day rewriting it 1,000 times, but it only took me a moment to tell you what to do. That's
right.
Compressible.
Yeah.
That's ordered. That's not complex. Laws are the same way. I can predict that the waves are going to go back and forth based on a whole bunch of physics principles over and over and over. That's predictable.
Yeah.
R, same kind of thing. Now, take, for example, a crystal, and we'll use a salt crystal, table salt. Okay. If you look at the structure of it, you'll see that it's predictable. It just basically alternates back and forth and makes a very perfect expected pattern. Mm-hmm. Now, I have a picture here of a cross section of a jet engine, some kind of aircraft. Don't know what this is. This exhibits something that's interesting. Is it complex? Yeah, it is. Is it ordered? In a way, it is also. Okay. This exhibits something known as specified complexity. So it's highly complex, but it's specific in the sense that it is necessary to function. There are a whole lot of other shapes that could have been attempted to make this thing work, and yet they wouldn't have. They have to be a particular angle in every blade, a particular distance from one another to operate. Yeah. There has to be a certain flow rate for the fuel to enter it for proper combustion. There has to be a particular density to the metal that's being used and a tolerance for heat, or none of these things will work. An example of this would be a book. Okay, a book is filled with words, okay? And these words make sentences and they make paragraphs and chapters and so on. And because of their sequence specificity, they convey a signal that's meaningful or necessary to function. Okay? Of all the things that you could fill into those spaces, only particular things are specific enough to perform a task. Functional DNA is the same way. Functional proteins are the same way. Not anything will work. So you have things that are merely complex. You have things that are merely ordered or specified. And then you have things that exhibit both complexity in one sense that they are incompressible. There's no way for you to simply describe what I just talked about here in this picture. And yet they are specific. They require this particular shape in a particular place and time to do what they do. That's specified complexity. It's a synonym for functional information. That's the distinction between the Scrabble letters that are just tossed around and the ones that are conveying a signal because of their sequence specificity. Right. Okay. It is also a synonym for information content versus mere information. So mere information would be Shannon information. Specified information would be information content bearing information. Right. So if I say specified complexity, I could be referring to specified information, functional information, or information content. Those all mean the same thing. So if I say, well, look at DNA and tell me, what kind of information does it exhibit? Is it Shannon information or is it specified information? It's specified, right? It's not just random stuff. Yeah. Everything it does takes a two-dimensional digital code, I should say like a one-dimensional digital code in essence, right? It's a string of letters, right, that produce 3D objects, right? And if you change just one of them, it won't work. If you change a couple of them, it really won't work. If you add or subtract one, and this is so frustrating when you talk to somebody who says, well, small changes over long periods become, what we know. This is how DNA grew itself, apparently. Mm-hmm. I try not to scream and say, you have no idea what you're talking about. Right. You've been lied to. Remember, a codon is a triplet. It takes 3 to create something. So if I have the sequence that has 10 codons, that's 30 nucleotide bases, and I add 1, do you see that all of them are now out of order? They all moved over by 1 position, which means that none of the other ones upstream from where I just placed that are going to read properly. Adding 1 destroys everything in the entire gene. You can't add 1. If you add 2, it does the same thing. They're all off by 2. You won't get the same amino acid. Yeah. If you add 3 and you actually put enough in there for a full codon, you still screwed it up because now it can't fold together properly. I see how just little changes over long periods of time. That's all it takes, Gavin. Okay. Yeah. Not a chance. Yeah. Not a chance. In the natural world, okay, meaning things other than the things that we create, specified complexity is found nowhere other than DNA, RNA, and proteins. That's it. You won't find it in the rocks. You're not going to find it, even though I believe God created those. You're not going to find it there. There's something unique about life,
Right.
that contains this. You'll find it in books. You'll find it in computer programs. And no one's disputing that. In fact, even people who disagree with me on where the information came from, at least admit this much: is that yes, it exhibits specified complexity.
Right.
Leslie Orgel, not a guy who agreed with us on anything, he did say this. He said, living organisms are distinguished by their specified complexity. Crystals fail to qualify as living because they lack complexity. Mixtures of random polymers fail to qualify because they lack specificity. So how did DNA arise? Well, we have three ways that events occur. They can happen by chance, they can happen by necessity, or they can happen by design, which is agency. That's creation. Now, here's a question. What good is that information without an information processing system? Okay. If I came over and I said, hey, there's a song I really want you to hear, check this out, and I hand you a cassette tape, what are you going to do with that? You're going to stare at me.
Right. I can't do anything.
You're going to ask me what it is, probably because we're from a different generation.
Yeah.
But I'm going to explain it to you, and you're still going to say, what can I do with this, dude? I don't have anything to, translate the information with and actually hear what's on it. I'll say, well, just take my word for it. It's a cool song. Okay.
Right.
The point is, you have to have an information processing system, or that information by itself is worthless. It wouldn't matter if you had it. You need something to read it. Okay, so what good is DNA without an information processing system? Well, since DNA doesn't do anything on its own, just like a cassette deck won't, the origin of life researchers have to explain, they're required to do this, the information processing system as well as the information. One does nothing without the other. So it's not as simple as saying, where did DNA come from? Even though, of course, that's the question we have here in the DNA enigma.
Right.
But it doesn't solve anything by itself. So remember earlier, I kind of stressed the fact that there's a major and a minor groove that move up and down that spine alternating on a DNA. The reason this is important is because due to these grooves, DNA cannot act as a direct template for proteins. You have an area where they would be able to contact something and an area where they would not, because they've moved away from whatever the template would require, right? They're too far from it in some places. They're touching in others, and then it just changes and alternates, which means that all that useful information in there, they'd be skipping every few little bits of it, and you'd have something that didn't work again. It's like removing, basically every couple digits out of your binary code. We're going to look just for a minute at RNA polymerase again. I want to talk about this. If you're at home listening to this, go Google it and see what this thing looks like. Okay, it's indescribable because it is complex, and you'll also see that it isn't just mere complexity, but it's specified, because what it's going to do is it's going to draw in, with the help of some other proteins, the DNA, split it, copy it, and then rewind it. I want you guys just to have a look at this thing. Now, in computer-aided drafting or computer-aided manufacturing, we start out with what is essentially a linear code, digital code, and produce 3D objects with it. So the cell does essentially the same thing. It has to convert from one digital form of information into another digital form of information. So what we're looking at here is this. The three-dimensional specificity of proteins depends on the one-dimensional specificity of DNA. The 4-character alphabet codes for the 20-character alphabet of amino acids, right? It starts from one, it's translated into another, and then it makes the protein. So any idea that you might get a direct template process somehow, that proteins came first, and therein lies the information that became later DNA, or in the opposite order, completely falls apart. You've got a set of codes that are changing between one and the other. There's a huge barrier there of complete language translation. You can't say that one is somehow from the other. It doesn't result from that. At least for its origin, it can't. Because we know that it certainly results in that, just not by origins.
Yeah.
So today we've got 3D printers. We've got all these different machines that will take this binary code and turn in all this different stuff. And so DNA does that, but here's what's unique about DNA that the other things don't. DNA doesn't just create things, it actually duplicates itself. Self-replication is something that no 3D printer can do. No CAD system, it does not matter, okay? Nothing will recreate itself, especially with the incredible specificity and the incredible precision that this does. So the RNA polymerase is going to bind to the start region, or what they call the promoter sequence, and it's going to have several of what they call protein subunits. It's not just one piece, it's a whole bunch of them. So it split copies, rewinds. The proteins promote or inhibit, depending on what's needed, the transcription of certain genes in response to whatever the cell needs. That's what they call, we mentioned this earlier, but they're called activator or repressor proteins. Introns are basically sections of the segments of your DNA that don't code for proteins. They are cut out of mRNA, and it requires a whole bunch of enzymes just to do that. So what people said is, well, hold on, if there's a section in there where, we're not using the code, what good is it? And of course, the evolutionists said, you know what it is? It's junk DNA. Where did it come from? Well, apparently some ancestors had it and they needed it for something we just don't because we've evolved past that. The problem is we've found uses for it. Sometimes it's used for operating system code. It doesn't make a protein. It just says, here's the timing and the sequence of all these other things so that that thing works. Right. And then, of course, they went from junk, RNA to junk DNA to junk proteins to all these other things. And you look at it and go, just because you didn't know what it didn't mean it didn't have a current purpose. There are certain genes that we've got that we'll probably never utilize because we just simply won't encounter a situation that requires them, but they're there just in case.
Right.
So because they're laying dormant doesn't mean that they came from ancestry or some nonsense like that.
Right.
Not to mention, if we're losing things, it's not a good argument to say that this is how we got it all. It's an example of loss if they even were correct about it, but we need gain to prove evolution. They have no examples of that.
Right.
Many enzymes fit together like puzzle pieces, and they assist RNA polymerase at the promoter sequence. The RNA is edited before translation at the ribosome, just in case it messes up. There's something called editosomes that actually go in there and double check the sequencing to make sure we didn't miss one, because that's a big miss. That's a huge problem if you get that. And by the way, all the things I'm describing are found in the simplest bacteria. Okay, so if you thought, well, you're talking about a relatively complex, modern, highly evolved cell. No, this entire thing, everything we've talked about so far, this entire segment of our creation series is on the simplest known bacteria. That's what I'm talking about. The process is even more complex if you move into eukaryotes. Okay, those are cells that have a nucleus in them. It only gets worse, not better. All right, guys, here's where this is going to take a turn to prove that God is the creator. All the parts in this process, everything that I've described, all the molecular machinery, okay, all the proteins must also be made from the code. They themselves are products of the code. RNA polymerase must transcribe code to make RNA polymerase. Understand? This thing does not exist except for by the product of translating its DNA.
Right.
And it's only the tip of the iceberg. So far, we've only transcribed DNA to RNA. That's all we've done. We haven't translated it yet at this point in the process. We talked about transfer ribonucleic acid, which is the little molecule that bonds to the RNA and on the other end helps to guide the essentially collision and then the bonding between amino acids to make the chain. For each one of those transfer RNAs exists a particular synthetase that's going to place the proper amino acid on the opposite end. Okay. Just because on the top it says, hey, I'm supposed to be, a particular amino acid doesn't mean that it's going to end up in the right place at random. There's actually a different protein whose job, or rather a synthetase, what they call amino acid transfer ribonucleic acid synthetase. And if you go online and look at a picture of it, you'll see how it puts everything together. It has to check and make sure that everything is proper so that it puts the right thing in the right place at the right time. They're highly specified themselves to recognize these particular amino acids. So think about this for a second. DNA copying, which is what we're talking about, requires many proteins. And it takes DNA to make the proteins. And it takes the proteins to make the DNA or duplicate it. They depend on one another. So how did this tightly integrated process begin? Well, one option was, of course, chance. The other would be necessity. And the third one is the obvious one. It was designed. Someone actually coded this. They wrote this and got the process starting.
Had to start the process, right?
Not only that, they had to not just start the coding, but they also had to have all of the parts for the process in the right place to let the code run. So in other words, the creator didn't just create the digital sequence necessary to keep it running, but all of the parts to read it and translate it into something useful. God made it when he said, let there be, just like that. Jacques Monod said in 1971, the code is meaningless unless translated. The modern cell's technology, let me just say this, guys. When someone refers to a modern cell, I'm like, they're all the same age. Don't tell me that. This is the kind of verbiage you got to be careful with. There's a lot of things they'll slip in there like that. And sometimes it goes past me too. But yeah, when they talk about, did you know, Braden, you're going to think this is crazy. You live here in Arizona. Did you know that rats, they're a rodent, right? Did you know that they're also related to javelinas? They're in the same family. Did you know that? And you start going, what do you mean the same family? That's a code word. That's a trick word for evolution. They're saying that they share some sort of common ancestry.
Right.
Look at them. You think those are a rat?
Right.
No, they're more like a type of pig, obviously. Okay. So people throw these things in, and here, of course, this guy's doing it. He says the code is meaningless unless translated. The modern cell's translating machinery consists of at least 50 macromolecular components, which are themselves coded in DNA. The code cannot be translated otherwise than by products of its translation. You get that? 50 macromolecular components. Each of these have, hundreds, if not thousands, of bits of information in them, right? Pieces of genetic code. And the problem is, he said that in 1971, and just to catch you up on where we stood when I created this slideshow something like 10 years ago, there's over 100 that are required. If you're missing one, it won't work. Richard Lewontin said this: what makes the proteins that are necessary to make the protein? David Goodsell said, what came first, proteins or protein synthesis? Good question, David. They came at the same time. Sir Karl Popper, he said this: what makes the origin of life and the genetic code a disturbing riddle is this: the code cannot be translated except by using certain products of its translation. This constitutes a really baffling circle, a vicious circle, it seems, for any attempt to form a model or a theory of the genesis of the genetic code. Well, Carl, you're right. This would be a disturbing riddle. The only disturbing thing about it would be that you face judgment from the one who created it. Run to him.
Yeah.
He's forgiving. He's forgiving of people like myself who used to believe that this happened by itself. So here's where it stands. The people who are doing origin of life research and don't just read the Bible and go, oh, there's the answer. They have to explain a few things. They have to explain DNA's ability to store information. They have to explain the origin of large amounts of functionally specified information and the origin of integrated complexity, meaning the information processing system. All of that has to be explained to say, well, this is how the ball got rolling because, what is life but something that self-replicates? Not like a crystal, but specified complexity. Crystals are not complex.
Yeah.
And the matter is interdisciplinary. So obviously mathematics is involved here. Statistics, which we're going to get into that probably more in the next episode. Classical information theory, just for measuring things and describing it. Physics, because of how everything's going to bond together, part of the chemistry involved there. Biology, clearly. And bioinformatics, which is the blend of these things. For my thoughts are not your thoughts. Neither are your ways, my ways, saith the Lord. For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts. Isaiah 55, 8-9. Scientists have the job of thinking God's thoughts after him. That was Johann Kepler. The old-fashioned word for introduction was general scholium. In the general scholium of Principia, which was written by Newton, it suggested that the stability of the planetary system depended not only on the regular action of universal gravitation, but also on the precise initial positioning of planets and comets in relation to the sun. He said, though these bodies may indeed preserve in their orbits by the mere laws of gravity, yet they could by no means have at first derived their regular position of the orbits themselves from those laws. Thus, this most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being, Isaac Newton. Well said.
Yeah.
Let's talk about cause and effect. In an attempt to explain past conditions, we use a distinctive mode of reasoning and infer past conditions and causes from what we call their manifest effects. In other words, we infer history from its results. Intelligent design, or I would call creation, because intelligent design tries to circumvent God, but I'm quoting a lot of things here from a book that I didn't write, is presently acting and causally adequate. Causal adequacy says this. If I said, let's walk outside, Brett, I want to show you something. Do you see how there's a bunch of water in your car right now and water all around it, but everything else is dry? Would it be safe to conclude that it rained or that I washed your car?
Wash my car.
Yeah. Because you say it's just not like adequate to say that rain just happened to go on my car and nothing else.
Right.
So there's certain things we look at for modes of explanation, even though we weren't there, and say, it's got to at least have some kind of causal adequacy. So minds are clearly capable of producing specified information. All the words we just used today, right? They're capable of producing it. The creation of new information is habitually associated with conscious activity. Not any information, specified information. So let me ask you, can you think of any other source than a mind that produces functionally specified content? There isn't one.
Right. Nothing.
Yeah.
Like the only thing is like a computer, but the computer is created by a mind.
Yeah. And it actually doesn't know what it's doing. That's why some of the information it spits out is, of course, it's going to lack what it needs. It's not going to function perfectly.
Right.
We'll go farther on the next one, guys. Thanks for hanging in there. Apologies again for my inability to convey this well, but hopefully you guys, if you want, go out and get the book that Stephen Meyer wrote, or get the audiobook version of it, and It's pretty amazing stuff. Just ignore him when he talks about the age of the earth. He's wrong on that, but great on everything else. And I'm certainly appreciative for what he's done. So thanks again, Braden.
Yeah, thank you, Gavin. And that was a lot of information to take in, but super good. And listeners, if you need to go back, re-listen to part 1, re-listen to this episode so you can take it all in, do the Google searches, put the time in to see what Gavin sees, to see what I see, just the beauty of God's hand in creation. Yeah. We thank you guys for listening to this episode of the It Stands Written podcast, and Lord willing, we will see you on the next one.